Welcome to the deep dive, where we take that fire hose of information you send us and basically distill it down into pure cognitive espresso. Today, we are strapping in for an astronomical challenge. But it's not really about looking up at the stars, it's more about looking at the current state of AI.
That's right. If you follow astronomy at all, you know we're kind of drowning in data. I mean, it's a good problem to have, but still. You've got surveys like the Vera Rubin Observatory's LSST, Gaia is still going. We're talking petabytes of new data every single year.
Just a staggering amount. And that volume means, well, manual human analysis just can't keep up anymore. It's past the breaking point. We need systems that do more than just, catalog things or spot simple patterns. We need, actual autonomous scientific discovery.
Exactly. So if you really want to test if an AI can think like a scientist, not just spit back facts, you don't give it some standard knowledge quiz like Astro or something. No, you pit it against the best young human minds on the planet. So today, our focus is a deep dive into how these state-of-the-art large language models, LLMs, how they actually performed on the International Olympiad on astronomy and astrophysics, the IOAA.
Right, the IOAA. And that feels like the perfect benchmark, doesn't it? Because it's not multiple choice. It really demands these multi-step derivations, complex, nonlinear reasoning. You need deep conceptual understanding. These are exactly the skills you need for actual cutting-edge astronomical research. It's definitely a marathon, not just a quick sprint.
And our mission for you today is really to unpack this central finding, which is, well, it's pretty astonishing. We looked at 5 top models, but the top 2, Gemini 2.5 Pro and GPT-5, they achieve what the researchers are calling gold medal performance on the theory exams. We're talking scores like 85.6% for Gemini, 84.2% for GPT-5.
Okay, let me just make sure I understand this correctly. A gold medal performance means they consistently ranked first or second, competing against 200 to 300 of the absolute smartest high school students from around the world, right? Across the 2022 to 2025 exams they looked at, they're basically operating at this elite competition-winning level.
That's the big headline, yes. But honestly, the real story, the interesting part, is in the details of how and where they failed.
Okay, let's definitely unpack that. But maybe before we dive into the failures, what exactly makes the IOAA so tough? And which parts of the exam did the LLMs actually take?
Right, a good question. The IOAA is pretty comprehensive. It usually has 3 main parts: theory, data analysis, and observation. Now, because LLMs are digital, this study focused on the 49 theory problems and the 8 data analysis problems from the 2022 through 2025 competitions. So that covers a huge range of physics, math, statistical analysis.
I have to jump in here, though, because whenever we talk about LLMs and these kinds of high-stakes tests, the big question is always data contamination. Did the models just memorize the answers somehow? Were they trained on this stuff?
That's absolutely a critical point, a fair skepticism. And the researchers knew this would come up. That's precisely why they made sure to include the IOAA 2025 problems. See, those exams were given in August 2025. That's significantly after the model's latest knowledge cutoff, which for most was around March 2025.
Okay. So the 2025 problems were essentially a clean, contamination-free test set.
Exactly. And the key thing is the model's scores on that specific exam pretty closely matched their average performance across all 4 years, which strongly suggests, this isn't just memorization. It points towards genuine problem-solving ability.
Okay, that does make the achievement seem much more solid, much more compelling. You mentioned they broke down the problems by difficulty, too. What did that show?
Yeah, they classified them based on the median scores of the human students. So you had easy, medium, hard, and even extra hard problems. Those extra hard ones, the median students scored below 10%. They're designed to stump pretty much everyone. And the models were tested across this whole spectrum, so they weren't just getting the easy stuff right.
Right. So let's circle back to those theory results then.
Yeah.
That 85%, 84%, how does that translate into a gold medal exactly? And how consistent was it year over year?
So getting a gold medal isn't just about hitting a certain percentage mark. It's defined as scoring, I think it's 60% higher than the median human competitor score across the whole test set. And these models, especially the top ones, didn't just scrape by. They really smashed it. All 5 models they looked at achieved gold medals in theory across most of the years evaluated.
Wow. So GPT-5 and Gemini 2.5 Pro were consistently up there, challenging for the #1 spot globally.
Absolutely, consistently. In fact, in 2022, 2023, and then again in that clean 2025 test set, GPT-5 actually scored higher than the single best human IOAA student in the world on those theory sections. I mean, it's kind of hard to overstate what that means for a piece of software.
Yeah, no kidding. I did notice something a bit strange in the data, though. A little footnote. It said GPT-5 actually did better on the hard questions than on the easy or medium ones. That seems backwards.
It does seem counterintuitive, yeah. GPT-5 got about 91.5% on hard questions, but then dropped to like 84.6% on medium and only 76.6% on easy. The researchers think this was partly due to just having fewer questions in the easier categories, so the sample size was small. But crucially, it also seemed to point towards some really catastrophic mistakes on tasks that involved conceptual geometry. Like in one specific easy geometry question from 2024, GPT-5 lost 18 points in one go, a huge area that basically tanked its average for that whole easy category.
Ah, okay. So those seemingly small errors, but on sort of fundamental conceptual tasks, that's the thread we can pull on. That seems like the perfect setup for the next part. Because when the models moved away from pure math, the abstract stuff, and towards problems needing like real-world visualization or interpreting actual data, that's where the cracks started showing.
Exactly. The difference in the data analysis results is probably the clearest sign of this structural weakness. Now, GPT-5, it managed to keep its gold status in data analysis too, scored around 88.5%, mostly because its multimodal processing is just better. But most of the other models, they saw a huge performance drop, like 10 to 15 percentage points lower than their theory scores. Big difference.
And why such a sharp drop specifically there?
Well, the data analysis exams lean really heavily on interpreting plots, reading messy charts, visualizing how data is distributed. It's not just about solving an equation on paper. You have to translate a visual thing into a mathematical parameter, or vice versa. And that's a task many models struggled with, unless they had really strong multimodal capabilities, like GPT-5 seems to.
And even staying within the theory section, you mentioned there was a big systematic gap already visible there. They were great at the high level, physics and math, category 2 you called it, but weaker on the spatial stuff.
Precisely. That difference, that 15 to 26 percentage point gap between the two categories, that's like the LLM's conceptual Achilles heel right now. They could nail the pure physics math problems, scoring up to 91%. Amazing. But then on geometric or spatial problems, category 1, their scores just plummeted, down into the 49% to 78% range. It really suggests they don't have a truly robust internal model of, like, 3D physical space.
Okay, this is where we get those really telling moments, right? The specific, almost basic errors that an AI capable of solving advanced cosmology still makes. Can you give us some of those specific examples, the surprising failures?
Yeah, let's start with spherical geometry. Seems fundamental to astronomy, right? Well, in an eclipse geometry problem from IOAA 2024, 3 of the models, and this includes top performers like Claude Opus and OpenAI o3, they made the same really elementary conceptual mistake. They basically assumed the sun, moon, and Earth were collinear during the eclipse, lined up in a straight line.
Wait, hang on. They assume they're in a straight line. That's completely wrong for understanding eclipse geometry. That's like flat Earth thinking. That assumption just invalidates the whole point of using spherical trigonometry, which they were supposed to do.
Exactly. It shows this profound lack of ability to really visualize the non-Euclidean 3D geometry of orbits and how things look on the celestial sphere. They might know the formulas, they can write them down, but they don't seem to grasp the basic physical setup.
That's incredible. It really is like watching a chess grandmaster suddenly forget how the knight moves. Just a fundamental piece missing.
That's a perfect analogy. And you see similar issues even in much simpler visualization tasks. There was a detector configuration problem, 2025 exam, pretty straightforward. Find an angle when some parameter, alpha, was 120 degrees. Most models got it wrong. They calculated 60 degrees instead of the correct 30 degrees. It's the kind of thing a human student would probably sketch on a piece of paper and immediately see the mistake.
Right. The machine doesn't have that intuitive visual check, that safety net.
Precisely. We also saw systematic confusion around timekeeping systems, basic astronomical timekeeping. Models getting confused between, say, tropical and sidereal years, making the wrong choice, or just sort of implicitly treating calendar years and tropical years as if they're identical, which they aren't for precise calculations. It seems like a context problem tied to understanding astronomical conventions, not just pure math.
And what about that multimodal disconnect you mentioned earlier, where they can state a physical law but can't recognize the picture of it?
Ah, yes, that one is maybe the most illuminating failure of all. It was a black body curve identification task. The models could perfectly articulate Wien's displacement law. They could explain it in text. Higher temperature means the peak wavelength gets shorter, intensity gets higher. They knew the theory.
Okay.
But then, when shown several graphs, they failed to reliably select the correct visual graph that actually represented that law. They had the equation, they had the description down cold, but they couldn't connect that text-based knowledge to the visual pattern recognition needed to pick the right curve out of a lineup.
Wow. That seems like a massive limitation if we expect these things to eventually process the actual images and graphs pouring out of telescopes like LSST.
It really highlights that the limitation isn't just about understanding text. It's about the model's fundamental ability to seamlessly integrate that theoretical knowledge with visual information and then apply that combined understanding to solve physical problems.
Okay, so summing this up, they're achieving gold medal results, in theory, which is incredible. But they're still filing down on seemingly basic geometry and visual tasks. What does this all mean for the future of AI and astronomy research? Are they ready to be our coworkers, or are they still just fancy calculators?
Well, the results are pretty clear on one thing. These LLMs possess genuine reasoning capabilities. They rival and sometimes beat extremely talented human competitors in complex theoretical domains. So that means they're absolutely powerful enough right now to serve as invaluable AI co-scientists.
An AI co-scientist,
Huh.
meaning they could, say, help verify complex derivations or explore the huge parameter spaces of new theories, or maybe cross-check concepts and calculations, basically speeding up the human research process.
Absolutely. They can be fantastic accelerators and double checkers for human experts. Help find errors, explore possibilities faster. But those critical gaps we talked about, the spatial visualization errors, the geometric reasoning failures, the trouble integrating text and visuals robustly, those gaps prevent them from functioning as fully autonomous AI research agents. At least not today.
Right, they can't quite run the lab on their own yet. Need some adult supervision, maybe.
Not yet, no. And the researchers were quite explicit about this. Before we can really hand over the keys to autonomous discovery in fields like astronomy, these fundamental limitations need to be addressed structurally. They suggest future work really needs to focus on implementing tools that kind of mimic human intuition. Things like visual sketch pads for the AI.
A visual sketchpad, like a way for the AI to literally draw itself a diagram of the sun, moon, and Earth so it doesn't assume they're in a straight line.
Exactly that kind of thing. Give it a way to manipulate spatial representations. And they also stress the need to synthesize huge amounts of visual question answering data, VQA data, that's needed to really improve that integrated multimodal understanding. Bridging that gap between text formalism and physical intuition is key.
So the core takeaway here seems to be that the journey from just recalling knowledge, even reasoning mathematically, to truly autonomous scientific thought. That journey is really defined by making the leap from the mathematical, the formal, to the visual, the physical, the intuitive.
That really feels like the cognitive boundary we're pushing up against right now.
And that actually leads us perfectly into our final provocative thought for you, the listener. Something to chew on. Think about this. We have an AI now that can win a gold medal solving problems in relativistic cosmology and stellar astrophysics. Incredibly complex stuff. Yet it fundamentally struggles with the kind of spatial visualization, the basic angle calculations that are pretty easy for a human high school student. This is classic Moravec's paradox, right? What's hard for us, complex math, is easy for AI. And what's easy for us, basic physical intuition, visualization, is incredibly hard for AI. So what does that actually tell us about the nature of intelligence itself, and what's it really going to take to bridge that final intuitive gap? Maybe think about what you find easiest to visualize versus what you find hardest to calculate. Where does your own intuition lie?
It's a fascinating contradiction to ponder, definitely.
Well, thank you for diving deep with us today. We'll catch you next time.